So let's look at the Fourier transform of a function which has been scaled in the time domain. So what we're interested in is a function f of t will give us a Fourier transform, and that will be a function of fi omega. But we're interested in a function of time which is scaled by a factor of a, so we're interested in the Fourier transform of the function f of at. So what's that Fourier transform going to be? Well, we'll start off, we'll have a look and see geometrically what happens whenever we add in this factor of a into this function, and we'll look at it after we've done it here. We'll look at it in the graphical calculator. So if we had a function f of t and its height 1 and crossover points minus 1 and 1, and let's say the value of a initially is greater than 0, so let's say for example the value of a is 2, so instead of a function f of t we'll have a function f of 2t. Now that has the effect of squeezing the function in the time domain, so the crossover points in this case would no longer be 1 minus 1, it would be minus a half and a half. Now the best way of proving that to yourself is just put in some values for t, and you'll be able to convince yourself that by adding on this factor of 2 or 3 or 4 it will squeeze this function f of t. Now we're also interested in the values for a which are between 0 and 1. In that case, let's say for example the value of a is a half, then that will have the effect of stretching the function. So if it was a value of f of a half t, then the crossover points would be at plus 2 and minus 2. Now there's one other option here, and we're interested in what happens whenever the value of a is less than 0. So let's look at that in the next slide. So if a is less than 0, let's say for example we have a value of minus 1 times t, then that has the effect of reflecting it in the y-axis. So this point here gets reflected over here, and this little section gets reflected over this direction. Now we could also make the value here greater than 1, or we could make it between minus 1, we make it between 0 and minus 1, in which case it would have the same effect of stretching and also compressing the function. So those are the three things we're going to look at, and we're going to have a wee look at them in the graphical calculator first of all before we go and work out the Fourier transform of this effect. So we'll look at our example of the time scaling in the graphical calculator using this little triangular function. So we can see our value of a is 1, so if our a increases to 2 then this should squeeze that function. Okay, so that's it, squeezing the function to a half, and as we move it further up this function gets further and further squeezed. Now if I come along the other way and get to a equals 0, then the function should just disappear. So that's the function gone, and as I work down in the opposite direction then you can see that the function starts to get squeezed again. Or if I go back the opposite direction, it starts to stretch. Okay, so what we want to do is we want to see what happens to a function of time in the frequency domain whenever we start to stretch and squeeze it. So let's have a wee look at that analytically. So let's look at the analytic derivation of the Fourier transform of a function which has been scaled in time. So if we had a function f of at and we wanted to find the Fourier transform, then we integrate it from minus infinity to infinity multiplied by e to the minus I omega t by dt. So what we're going to do is something you'll see in a few of the videos to come up, and that is going to be our substitution. So we can replace this value of a of t with a factor of x. We can then say that t must equal x upon a, and if we were to differentiate both sides, well, a is just a constant, so it would remain the same. So we'd have a dt would equal dx upon a. Now if we look at initially for the values of a greater than 0 and we substitute these in, then we can say our value of at becomes a value of x. We can see that the value dt becomes dx upon a, and we can see the value of t is going to become x upon a. So we get this line here. Now we'll take out the value of 1 upon a and we're left with this here, and that's the value of a greater than 0. Now we can do the same thing for values of a less than 0 and we'll get this function here. So we can see then that for all values of a, if we take the absolute value of a there, so it'll be 1 upon the absolute value of a times the integral from minus infinity to infinity of our function here. Now what we'll do is we'll replace the x again with a value of t, so we'll just be left with this equation here. Now this equation here is just 1 upon the modular, the absolute value of a, and what we have here is the Fourier transform, but it's a Fourier transform not of the function I omega, it's going to be the Fourier transform of the function of I omega upon a. So this is the transform pair we've been looking for. The Fourier transform of a scaled function in time is equal to 1 upon the modulus of the scaling factor times the Fourier transform of the function divided by that scaling factor. So here's an example of using that Fourier transform pair. If we had a little square function here in the time domain, we know we get this sinc function in the frequency domain. The height is going to be tau, and the crossover point here is going to be, the first one will be 2 pi upon tau, so each of them will be values of n pi upon tau, that's where the crossovers occur. So then if we were to scale this by a factor of 2, so now we've got f of 2t, then it's equivalent to squeezing this down, so that's the function we get here. So we're saying then that the Fourier transform of that's going to be 1 upon the absolute value of the scaling factor, which is 1 upon 2, so we end up with our tau upon 2, and for here we'll end up with our sine omega tau upon 4, all upon omega tau upon 4. So this is the effect of stretching out this function here, the sinc function. So now the crossover points are going to be at 4 pi upon tau, so each of the crossover points will be a factor of n 4 pi upon tau, and the height here is going to be halved. Now the height is going to be tau by 2. Now you can do the exact same thing in the frequency domain. We won't draw it out here, but you get the similar results. If we had our function I omega in the frequency domain and we scaled it by a factor of b, then in time domain that would be equivalent to a function of 1 upon the absolute value of b times the function of time divided by b. So that's all there is for the frequency scaling. We'll go through a few examples in the example section. So thank you for listening and goodbye.